In this video, we are going to be introducing the concept of an ellipse. So as you can see from the picture in front of us, an ellipse is sort of an elongated circle where one of the, directions seems like it's bigger than the other direction. So with that in mind, let's establish how an ellipse actually gets created. So we start with 2 points, and those points are called foci, or foci, which is the plural of focus. So plural of focus. In our picture, those 2 points would be this point right here that we see at -4, 0, and this point over here that we see at +4, 0. We'll use F for foci. So what we do to create an ellipse is we take the set of all points where if you take the point and you add up the distance from this point to both of the foci, then that distance, oh boy, that's a straight line, all right. Then that distance is going to be the same regardless of the point that you pick that's on the ellipse itself. So those two distances added together are going to be the same all the way throughout. Doesn't matter where you pick the point on the ellipse. So with those things in mind, some other points that are going to be of interest here. We should talk about it. Splits it into two different axes, a horizontal axis and a vertical axis. The longer of the two axes is going to be known as the major axis. So major axis, this is the longer axis. By longer, I mean the distance from the middle of the ellipse, called the center, out to the ellipse along that axis is as long as it can possibly be. So in this case, we would say that this is the horizontal major axis. The shorter axis in this case would be the vertical axis. That is known as the minor axis. This will be the shorter axis. And by shorter, I mean the distance from the middle of the ellipse out to the point on there is as short as possible on the actual ellipse. In this case, that would be a vertical minor axis. If you were interested in seeing what a vertical major axis looks like, well, that would look just like this, where it is longer in the vertical direction than it is in the horizontal direction. Other key points to know, the point that's right in the middle here, we'll refer to this as C. Capital C is referring to the center. That's the point that's right in the middle of everything. And finally, the extreme points along the major axis have a special name as well. Each one of those individually is referred to as a vertex. Vertex. Or if you wanted to pluralize that, they would be vertices. Now, with those things in mind, there are a couple of important distances that are associated with all of these. Oh, sorry, there are also 2 more points. The corresponding points on the minor axis also have special names. They are called covertices. So we'll say CV is a covertex. Or if you wanted to pluralize that one, they would be covertices. So there are some significant distances along the ellipse as well, and we'll go ahead and label those. So this labeling system is going to be consistent for both ellipses as well as hyperbolas, but we'll see that as we continue onward. So the first distance that we have is going to be referred to as little a. That is going to be the distance from the center to a vertex. I probably could have just said C here, but center to vertex. So in actual picture here, let's grab this one. This one's a little thicker. So this distance from the center all the way out to this vertex, that distance is going to be referred to as little a. Additionally, if we go along the minor axis and do the same thing, we'll refer to that distance as b. So that's the distance from the center to a covertex. So in this case, that would be from the center to the covertex, this distance right here, this would be known as b. Now, this is also true from the center to the other vertex or the center to the other covertex. Those are still known as a and b. And final one, let's see if we have room all the way down here at the bottom. Last distance is going to be referred to as C. This will be the distance from the center to a focus. So in this case, that would be, I guess, from here to here. We could label that center to a focus. That'll be C. Now, with the already drawn ellipse, it's a lot easier to see this concept already, but hopefully this explanation will make sense as well. Of these three distances of A, B, and C, there is a guaranteed largest one. Now, the guaranteed largest one, if we were to compare A with B, A is on the major axis and B is on the minor axis. Major has to be bigger than minor, or else it would be the other way around. So we can definitely say that A is greater than B because major is bigger than minor. Additionally, because an ellipse has its foci on the inside, it is guaranteed that the distance A out to the vertex is going to be greater than the distance to the focus. So in that regard, A is definitely going to be greater than C. So of the three quantities, A, B, and C, A is guaranteed to be the biggest. A is biggest. Now, there is another relationship that exists among A, B, and C, and it is actually the Pythagorean theorem. We're not going to go into the proof in this video, but it's a doozy. So here's the thing that's kind of infuriating, though. In a right triangle, C is the biggest because C represents the hypotenuse. In an ellipse, A is the biggest because, well, we just said why A has to be the biggest. So the Pythagorean theorem, as it applies to the ellipse, actually looks like this. A squared is equal to B squared plus C squared. If this infuriates you, good. It infuriates me as well. But it is with very good cause why we do this, and that'll be explained in the section on hyperbolas.